Alright, what's up everyone? Welcome back to Structure Free Learning. And in this video we do our third example problem on the method of virtual work for beams. And hopefully you have observed the other two and you're very familiar with the process by now. And over here on the right, what I've done is just give you or written out the formulations for the method of virtual work that's most used for beams. Down below is the general process or approach that I like to do when I'm trying to solve problems using the method of virtual work. So in this example, what we have is a simply supported beam with a uniformly distributed load, very popular condition that you've probably analyzed since the beginning of statics. And in this case, EI, or the flexural rigidity, is constant. And what we want to find are the slopes at point A and the deflection at midspan. And the first thing I like to do when I'm doing this is establish a coordinate system. And this coordinate system gives me a sense of what I consider to be a positive deflection for the elastic curve and a positive rotation for the elastic curve, positive or negative. And so I'm just going to have my origin at point A on this beam, have x going to the right, positive x, and positive v upwards. Next, I want to draw the internal shear and moment diagrams for the real loading. For this simply supported beam, hopefully you're pretty familiar with the shear and moment diagrams of a simply supported beam. But if you're not, you've got to follow that process of calculating the reactions. And here you want to draw that free body diagram first. And then use equilibrium equations to solve for this reactions. If you did some of the forces in the horizontal, this would be 0. You could do moments. I know by symmetry that AY and CY are equal and take half of this distributed load. So 5 times 6 is 30, or 5 times 12 is 60, and AY takes half of that 60, which is going to be 30 kilonewtons, and this will be 30 kilonewtons. Now I can go ahead and draw the shear and moment diagrams. I have a uniform or constant distributed load, meaning I'm going to have a linear shear, and the shear is going to start at 30 kilonewtons up here and then decrease linearly to negative 30 down here. And my moment diagram will be parabolic since my shear diagram is linear, and this value here is equal to this area, which is 1/2 6 meters times 30 kilonewtons, which makes this 90 kilonewton meters. Now, if you've watched the previous videos or the previous examples, then you know that I consider this real moment diagram to really be a curvature. And so since I have a constant EI, really what we're doing with this real moment diagram is coming up with a curvature diagram. So I'm going to call this M over EI. And all these values will be divided by EI. Now we're ready to look at the virtual structure with the virtual loading and get virtual shear and moment diagrams. And the first thing I'm going to do is concentrate on the slope at point A. When I'm trying to figure out the slope at A, I've got to apply a external virtual unit load at point A, and because I'm trying to find a rotation, I've got to apply a unit moment. This is what my external virtual structure will look like. I'll do it over here on the right. And at point A, I'm going to apply an external virtual unit load or a moment, and it's going to be like this. I'm going to call this 1 kilonewton meter. I've just assumed that this rotation at A is going clockwise. You could have drawn it counterclockwise, and you'll find that when you calculate the result, the signs will correct itself. But this is my virtual structure here. Then we want to find the shear and moment diagrams of the virtual structure. And again, that involves a free body diagram, equilibrium equations for reactions, and then drawing the shear and moment diagram. So here, I'll call this A prime Y, C prime Y, and then a horizontal AX prime. And I know from some of the forces in the horizontal this would be 0. And I'm going to use some equilibrium equations. So if I take moments about point A equal to 0, right here, I would have minus 1 kilonewton meter plus CY prime times 12 meters equal to 0. And when I solve this out, this will tell me that CY is equal to 1/12 kilonewtons. And then from some of the forces in the vertical, I have AY plus CY equals 0, which means AY is equal to negative 1/12 kilonewtons, which really just means that AY is 1/12 kilonewtons and it actually should be pointing downwards. And so when I draw the shear and moment diagrams, I'm going to start at negative 1/12, and because I have no loading in between, it's just going to be a constant shear that goes straight across. My moment diagram, I'm going to start here at positive 1 kilonewton meter because I have a concentrated moment at A, and it's going to be decreasing linearly to 0, or at a rate of 1/12 kilonewton meter per meter. And so over 12 meters, that's a change of 1, and bam, that should have been a 0. You can calculate this area right here, which would have been 1/12 times this length, which is 12 meters, and would have told you that the change in moment that we experience over here should be negative 1 kilonewton meter, which takes us down to 0. Alright, so there are my moment diagrams. Here's my real up here, my real moment diagram, and this, or my real curvature if you will, and here is my internal virtual moment diagram. Now we're ready to apply the principle of virtual work and integrate and solve for the displacement, or in this case the slope at A. And so 5. And the basic premise, as always, behind the principle of virtual work is that the external virtual work is equal to the internal virtual work. With us trying to solve for the slope, we have the unit virtual moment times the real displacement at A is equal to the integral over the entire length of the beam, m prime, which is the virtual moment, times the curvature, real curvature, dx. Basically, I have one moment function to describe each moment diagram. So I have one function to describe the virtual moment diagram, and I can use just one function to describe the real moment diagram. I could go ahead and apply moment functions. That's one option. The other thing you can do is use product integration tables and solve them using charts that are available. So I have a textbook, and when I look inside this textbook over here, I find that, let's see, a triangle that looks like this and a parabola that looks like this, and when I integrate the two together, the integration product of these two functions is equal to 1/3 ABL. And so what I like to do is go ahead and just kind of draw for myself what this integral looks like from 0 to 12 meters being the entire length, and this m prime was the virtual moment diagram, which looks like this, had a value of 1 kilonewton meter. This was 12 meters, and then my real curvature is 90 over EI over 12 meters. And so when I apply this 1/3 ABL, I have 1/3 A, which is 90 over EI kilonewton meters, times 1 kilonewton meter times 12 meters. And this, let's see, I'll have some units canceling out, bam, bam, and this would tell me that theta A is equal to a positive 360 over EI kilonewton meter squared. And this thing, if you substituted values for E and I, that's going to come out to the same type of units, or kilonewton meter squared, assuming you use the proper units. And then this theta A will be dimensionless, which means it's going to be in radians. Now, this positive value just indicates that this 360 EI kilonewton meter squared rotation is also in the same direction that we drew that virtual unit moment, which is clockwise. According to our sign convention that we set up, this V and X, and point A rotating like this is actually a negative slope in this VX beam, local beam coordinate system. And so if I were to describe the slope at A according to those VX coordinates, that would be that dV dx at 0, or theta at 0, because that's what theta at x equals 0, this would be negative 360 over EI kilonewton meter squared. But both of these answers would be acceptable depending on how the question is worded.